What if we could see inside a chemical reactor? Not just the fluids rushing through, but every single particle colliding, mixing, and reacting. That's the promise of Computational Fluid Dynamics Discrete Element Method, or we can call it CFD-DEM, a powerful computational tool that is transforming how we design and understand chemical processes. For decades, engineers relied on experiments and simplified models to predict how gases, liquids, and solids behave together. But multiphase systems, like fluidized beds, dryers, or gasifiers, are notoriously complex. They involve millions of tiny particles interacting with turbulent flows. Experiments give us snapshots, but they can't capture everything. That's where computational fluid dynamics combined with discrete element method, or we can call it CFD-DEM, comes in. Together, they allow us to simulate the invisible dance between fluids and particles at multiple scales. The main objective of CFD-DEM research is simple but ambitious: to bridge the gap between microscopic particle interactions and macroscopic reactor performance. In other words, how do billions of particle-scale collisions shape the overall efficiency of a reactor? By combining the Eulerian description of fluids with the Lagrangian tracking of individual particles, CFD-DEM provides a window into this hidden world. So, how does it work? Think of the fluid phase as a continuous field, described by averaged Navier-Stokes equations. Now imagine each particle tracked one by one, like tiny marbles moving under Newton's laws. At every time step, the two worlds exchange information. The fluid pushes on the particles through drag, lift, or buoyancy forces, while the particles push back, altering porosity, turbulence, and flow patterns. This back and forth is the essence of Eulerian Lagrangian coupling. Of course, reality is messy and researchers make choices about resolution. At the microscale, direct simulations can resolve flow around each particle, but this is extremely expensive. At the mesoscale, we average over cells large enough to hold many particles, but small enough to capture clusters or bubbles. And at the macro scale, models boil down to bulk behavior, like pressure drop. Computational fluid dynamics coupled with discrete element method usually lives in the sweet spot: fluid on the mesoscale, particles on the microscale. This balance gives us detail without making computations impossible. Now, what have scientists learned using computational fluid dynamics coupled with discrete element method? Scientists highlighted its applications across chemical engineering. In drying, the method predicts how heat and moisture move between fluid and particles. In coating and granulation, it reveals how collisions distribute material over particle surfaces. In mixing, it helps us quantify segregation, where heavier or larger particles drift away from lighter ones. And in high temperature processes, combustion, gasification, pyrolysis, computational fluid dynamics coupled with discrete element method uncovers how chemical reactions couple with flow and particle motion. The key findings are striking. Computational fluid dynamics coupled with discrete element method can track not only velocities and pressures, but also residence times, contact forces, bubble formation, and segregation indices, quantities that experiments struggle to measure directly. For instance, simulations can reveal how local hotspots form in a fluidized bed, or how attrition grinds particles down over time. These insights guide engineers in optimizing reactor design, scaling up processes, and reducing costly trial and error. The impact of this work is broad. In industry, fluidized beds produce fuels, polymers, and pharmaceuticals. Understanding bubble dynamics can mean higher efficiency and fewer emissions. In energy, gasification and combustion simulations support cleaner power generation. Even in emerging areas like carbon capture, advanced computational fluid dynamics coupled with discrete element method helps design more reliable reactors. Beyond chemical engineering, the same methods extend to pharmaceuticals, food processing, and even geophysical flows like sediment transport. So, what should you take away? First, computational fluid dynamics coupled with discrete element method is not just a modeling trick, it is a bridge between particle scale physics and industrial scale performance. Second, it offers unique insights that experiments alone cannot capture, especially in harsh or opaque systems. And third, While computational cost remains a challenge, advances in algorithms and high-performance computing are pushing the limits every year. To wrap up, computational fluid dynamics coupled with discrete element method reminds us that the microscopic world of particles shapes the macroscopic world we live in. By combining physics, mathematics, and computer power, we can simulate the unseen and design smarter, cleaner, and more efficient processes. If you found this quick overview interesting, stay tuned. I'll be breaking down more cutting-edge research papers into clear, engaging lectures. Curiosity is the best fuel for science, and there's always more to explore.